set and a testing set, right?
Mhm.
So the new testing set that we're making is that to go above and beyond the.
Well, it's kind of interesting. The test set doesn't actually have information on the survive. It has one less variable, so it doesn't even have survive. So I think the idea is that you'll create a model, hopefully like cross-validate or bootstrap or whatever you want to do your results, and then submit it online, and they'll check it against the test set. So they have a test set in which they're like the whole idea of the Kaggle challenge is to be as accurate as possible, and if you have all the data, you can just cheat. So, which they still do cheat. But yeah, so we're just going to use the train data for this. And then I think I've explained this, but I want to make sure that it's crystal clear. The idea of what we're trying to do with this project is to be able to create a model that predicts whether or not an individual is going to survive. And we want to be able to test how accurate our model is, which we'll do in a little bit, and see to what degree of accuracy we can get to. So let's go ahead and build our model here. Oh, actually, yeah, that's a great idea. Yeah.
Nice cool down for their brains.
Yeah, a lot of information. Yeah, that was kind of the bulk of the thought process. So the rest of it's pretty mechanical.
So does anyone have any questions or got stuck anywhere along the way?
Okay, so getting back into it. So now we're going to get kind of into just the mechanical, not so much thinking involved. We're going to define our formula for logistic regression. We'll just call it formula. I already have it defined. But formula, and then arrow sign dash, that kind of defines this new formula that we're going to add in. The first one is going to be your dependent variable. And then you'll want to do tilde. Tilde is on the top left, shift, whatever that thing is up there. And then what you'll want to include is P class plus sex plus age plus SIB, make sure you get the capitalization right there. We're going to get sex times P class. Remember, we looked at that interaction toward the beginning of the, what do you want to call this, lecture? And we determined that there was some pretty significant workshop. That's what we're calling it. Crash course, yeah. And then we got PARCH, parent-child, times age, which is another type of interaction that we found was pretty, not that. Go ahead and run that. So now we have our formula defined. Let's go ahead and run a regression based on our formula. So we'll go ahead and call it model.1. That same little equals GLM formula equals formula data equals df.train. Then you're going to want train, comma.
Alan, you good? You good?
Yeah. That look better? And then family equals binomial. So I'll explain all that here in a second.
How do you define a formula? Like, why do you put those terms there, like in that way?
Within GLM?
No, the formula.
Up top here?
Yeah.
Yeah, so I'll get into that here. So basically, we're just creating a... Yeah, I suppose that I probably should have talked about that. We're creating a logistic regression based on what we think is going to be important. And that's honestly half the battle. Yeah, I definitely totally forgot to talk about that. we want to find what we think is going to be an important indicator on your probability to survive. Some of this, they kind of intentionally made this data a little bit messy. Not all of it is super useful. Their passenger ID maybe doesn't tell all that much about who they are. It's just, the time at which they bought the ticket. The ticket itself maybe has some information if you are able to, sparse through the Titanic's ticketing and figure out further information about the tickets. But just in this table doesn't really say a whole lot. We have no reason to believe that 17,000 has any meaning as opposed to 330,000. We have no real reason to think that there's any difference between the two. So we didn't include that. We didn't include survived. Cabin is missing tons of information. So we didn't include that. But others we can think would definitely have a lot of information. The class that they're in. If they're in first class, maybe they have a higher chance of surviving. We looked at the earlier exploration and figured that out. But that's kind of part of the data exploration side of things, to incorporate things that you might think are significant. Go ahead.
Can you explain more about the interaction time?
Yeah, so that's basically, so if you have each individual dummy variable, it'll look like this. You have P class 1, 2, 3. So that if you ran P class and sex separately, then it would have no further insight as to whether a first class woman is more likely to survive than a second class woman. So creating interaction terms basically just looks at those further insights rather than just class or just sex. Let's see, where were we? Okay. So once you type this out, you can run this. You'll have your model, and then we'll want to look at the model. So go ahead and type out summary, parentheses, model.1. Run that. And then you'll see that you get a nice little regression table here. And if you've ever taken a class on linear regression, this might look pretty familiar to you. Is there anybody who has not taken a class on linear regression, or maybe this regression table is not making a whole lot of sense to you? Perfect. So what's going on here is we have each of the dependent variables in our regression. So we're interested in figuring out what the relationship between each of these dependent variables is on your log odds to survive. Remember, not probability, log odds. So we're looking at these estimates of the coefficients. You'll see that some of them are positive, some of them are negative, some are relatively large, some are relatively small. This tells us the degree to which each has an effect on the log odds. So if somebody is a male, their log odds are 5.955 lower than if they were a woman. For each year you get older, there's a general negative trend in age on your probability to survive. So it looks like the youth have an advantage against the more elderly. I didn't end up using the groupings for age, which maybe I should have, but for right now, don't worry about it too much. So this tells you the general effect on the log odds, which, like I said, is a little bit hard to interpret. What exactly is one more log odds than another? But just think of it as your probability. Like it's increased, because if it's negative, then your probability doesn't decrease. The right side, we have this PR, blah, 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 blah. That's your p-value, and it tells you how significant each relationship is. The lower the number, the more significant the relationship. These stars tell you to what degree each is significant. A period's not super significant. Stars, fairly significant. 3 stars, super significant. So we can say with a great degree of certainty that P class is very significantly negative. When I say significant, I don't mean scale. I don't mean very largely negative. I just mean we're very sure that it is negative. So that's kind of, and then don't really worry about standard error and z-value. They can all be derived based on your p-value. So p-value is kind of a little shortcut. Yeah, so for this one I was toying around with this before. Like I said, didn't realize I was giving this presentation until yesterday. And this should be a series of dummy variables. There should be 5 of them. There are 6 different possibilities for p-class sex because 3 classes times 2 sexes is 6. So for dummy variables, you always have 1 less. And I wasn't getting results I liked, so I kind of stuck with this one, which is probably not what you should do, but probably not what you should do. But right now, don't worry about it too much. There's a lot you can interpret from this. All right, so we got a little. Yeah, go ahead.
So when you use GLM, it's all
Oh yeah, I forgot to explain that part. So if you've ever ran regressions in R, you might have used LM. A lot of people who do their regression in other languages, but in R you typically use LM. LM stands for linear models. So it essentially, just as long as you put in the right input in here, it runs a linear regression. GLM is generalized linear models, which contains a set of different linear regressions. Logistic regression is a type of linear regression. So you're using GLM, which contains a set of linear models. And then at the end, you can see that I said family equals binomial. And that just specifies which model I want to use. Logistic regression is a form of binary classification. So I said family equals binomial. Now R knows that GLM, I'm wanting to use the logistic regression.
Are those variables long-term?
As dependent variables or independent variables on the right, they're not log. That's a whole nother situation that I can talk to you about later on, because I'm not going to do that right now. But yeah, sometimes you'll want to transform your right variables. You might want to log them, you might want to square them, might want to cube them, and they'll give you some different interpretability, which has some nice properties, which we can talk about later. If you know anything about heteroscedasticity, that's one of them. So now that we've estimated our logistic regression, we can use our logistic regression to predict on the rest of the training set. Remember that when I drew that, logistic regression, it had that S shape. And we said that anything above the S shape is 1, anything below is 0. So right now, all we have is the line. So now we need to tell R that anything above the line is 1 and anything below is 0. So let's go do that. So you're under predict on the rest of the training set. We're going to go, there's a decent amount of code here, so bear with me. cv.probs predict, parentheses, model 1, that's the logistic regression that we just created, comma, new data equals df.train negative train, comma, and then close the bracket. So I'll pause for a sec. Remember before when we split the data into training and test data, we wanted to learn the relationships based on the training data and leave the test data alone. We're not going to worry about the test data for now until we have our regression. So we did our regression on all of the training data. We learned a relationship. Now we're going to use the rest of the data to test whether or not our regression was significant. Well, not significant, accurate. So by putting new data equals df.train, we are predicting against the rest of the data. Sorry, is it too small again?
I was just wondering if that's a tilde or a dash.
The negative sign right here. Yeah.
Oh, okay. Yeah. So the negative sign is it's basically the complement.
The rest of it, yeah, the complement, yeah. And then we're going to go still inside the parentheses. Type equals response. Response is in quotations, comma, na.action equals na.pass. To be honest, I'm not entirely sure about this last piece here, but I know that it completes the line of code to predict, so fortunately I can't help too much with that. And then, so now we have our prediction, and we can take a look at the top of the prediction. So if we use the head command, we'll be able to see the top 5 or 6 of what we just defined. So we just defined cv.probs. CV is our cross-validated probability. And we'll be able to see that now passenger ID 2, 5, 7, 9, 13, and 15, we'll be able to see what their probability is. So we converted our logistic regression into probabilities. So now we can give that 50% cutoff line based on that logistic regression line that we put. So now we can convert those probabilities based on the logistic regression into predictions. So these next 2 lines, just go ahead and run those. This creates a prediction. So this creates a new column, which is predictions. So up here we have passenger ID, survived, P-class, blah, 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 blah. So now a new column is going to be your predicted survived. I don't think I attached it into the data frame, but I probably should have. So now we'll be able to see, hopefully, our prediction will be pretty similar to survived all the way along. If this is 0, we'd hope that our predicted survive is 0. If these 3 are 1, we'd hope that they're 1 as much of the time as possible. So now we'll define this new function, which extracts the true cross-validated response. This just tells us whether or not, actually, what is this one doing again? I don't exactly remember. In order to diagnose the model to determine at what percentage we actually were correct, these next few lines of code just returns back how often we were correct. So we won't go over that tonight, but go ahead and ask questions after if you have any. So run the next 3, and then in this next one, we can now try and figure out how our model performed. So here we're going to use the table command, table parentheses cv.predictions y. And so what this is going to do is this is going to build us a table that contains the amount predicted of survive and not survive for each individual observation, and then compare it to what actually happened. So go ahead and run it and you'll see what I'm talking about. And this pulls up what we call a confusion matrix. So you can see that on the top here we have the predictions 0 and 1. So here this contains all which we predicted would not survive, all which we predicted would survive. The rows indicate what actually happened. Did they die? Did they survive? So 0, 0 means that we predicted that they'd die and they actually died. 0, 1 means we predicted they'd die but not correctly. Those 5 actually survived. So it's a false negative. Here we have a false positive because we predicted that they'd survive 29 times that they actually died. So we incorrectly predicted that, but we correctly predicted survival 38 times. So then we can figure out what our error percentage and accuracy percentage is. These next two just sum up errors divided by total observations, and then total observations, or correct predictions divided by total observations, if that makes sense. So here, based on the model that we just ran, our classification error is 0.19, and our classification accuracy is about 0.81. So that means that we just built a model that correctly predicted 81% of the time. That's not too bad. That's not too bad. If you came 2 weeks ago, I threw together a quick little logistic regression which predicted 52% of the time correctly. That's not very good. Yeah, 52% of the time, you may as well guess. You may as well just use means at that point. You may as well just look. We looked at the very top. Means is a form, is an algorithm. Like just looking at means, we found the mean of how many people survived, and we said 38% of the time they survive. So we'll just randomly pick 38% of the time that you'll survive, and what is that? 62% of the time that you'll die. And that's an algorithm. It's not a very good one, but it's one of them. Here, we correctly predicted 81% of the time. So that's pretty cool. You can go ahead and like save this, upload it onto Kaggle, and you can get feedback on it. You can get people telling you. You can compare your results with other people's, because on Kaggle's, here, I think I have it pulled up somewhere. Not that one. This one. Yeah, right here. You can go up to kernels and figure out what other people did. So let's click on here, this top one. So this guy wrote up a little paper thing. Yeah, it looks like he did his in Python, which is okay. And you can look at all the stuff he did, a lot of similar things. Find a lot more insights. I did some very basic insights at the very beginning, very basic data exploration. But I encourage you to go on Kaggle, look at what other people did, compare it against what you did, and see what you can learn. Because this is really just kind of a very basic overview of, you know, the types of things that you can do. But right now, you guys just deployed a machine learning algorithm.